So the topic, once again, quantum circuits and identities. So I'll try to recap the stuff we went over last time. So this is sort of like a high-level refresher of what we went over last time. So we went over one of the first things I started with was like understanding why it's so important to really understand the underlying quantum mechanics. Now I understand like a lot of existing resources where they teach you quantum computing, they are incredibly motivated not to tell you the underlying quantum mechanics. The reason being is it's very easy to go down that rabbit hole and kind of forget what the relationship is. But I think I proved to you guys last time there was this relationship between the wave function, which defines every quantum state, or every quantum system, and note that I'm still hesitant to use the term particle here, because there are multi-particle quantum systems as well, or even macroscopic systems that exhibit quantum behavior. So larger molecules can even obey this wave function. And the wave function, as we remember from last time, it's complex valued. By itself, it does not mean anything. You just put in some variables, you get some complex value out. So we have to do a little bit of manipulation there to really make sense of the wave function and see the kind of data that it encapsulates. But out of that wave function, we did notice that a natural consequence of that function is that energy levels are quantized. So the eigenstates, as we would call them. And these help dictate properties like superposition, where we can have like a linear combination between two energy eigenstates. We also went through bracket notation, and those quantum gates, we represent those as matrices. So you remember your brackets are vectors, like the ones here. I have a little example here, but your quantum gates are matrices, and for the most part, that's what we're going to focus on for today. So within bracket notation, there are two sort of parts to it. Like you notice the funky little spelling here is because we have bras and we have kets. And a ket is nothing more than it's just a vector. That's literally what it's used to represent, and it's just used to represent a certain quantum state. And what I mentioned earlier is that I could take a linear combination of these energy states, or the eigenstates, and I could come up with another equally valid quantum state. So in quantum computing, we prefer to choose two sort of basis vectors, 0 and 1. And with them, we have these coefficients alpha and beta, and we can generate any other kind of superposition between the two that we're interested in. So it's just sort of like a mix, a little bit of 0 and some amount of 1. And if you'll remember from last time, there is a condition on alpha and beta, which requires that the vector be normalized to length 1. So I can't just put some combination here. Is ket only the column vector? Yes, that is correct. That is one way to think of it. So the kets are here; they're the column vectors, and then your bras are the row vectors. That is correct. Someone asked in the chat here. That's a very good distinction and a very important distinction as we see the counterpart to the ket, which is the bra. So thank you very much for asking that. Now the bra is what we call the Hermitian conjugate of a ket. So what exactly is the Hermitian conjugate? So we have the ket here, and you notice that for a Hermitian conjugate, the conjugate of a complex number, you will take that center symbol, if it's positive or negative, and you'll flip it. But you'll notice that for these basis kets, there are no complex components. So, performing a conjugate just, doesn't really change anything. But what does change is the dimension. So now we have to perform this transpose where we take the rows and they become columns. So this row 1, row 2 becomes column 1 and column 2. So that's the bra, this ket, and that's the bra. In fact, one of the rules for bracket notation is that every ket is guaranteed a bra, and vice versa. Every bra is guaranteed a ket, just because of the nature of the conjugate transpose. The bra was something I introduced last time, but I intentionally kind of omitted the reason for why we have it. Like, you understand pretty intuitively why we need kets, to represent these mixed quantum states or superposition states. But I did not, mention like there's this bra mathematical tool, but where does it fit in the context of, of quantum computing? And it has to do with measurements and how we perform the ability, like when we collapse superposition. So, we're going to lose that superposition state on measurement. So basically, here's the block sphere. This is just a way it's a very nice tool in visualizing a superposition state. So you notice that have 0 on this part of the sphere and 1 at the opposite direction. And we can have the vector, which I remind you again is constrained to be length 1, and that vector, that state vector as it's called, can sort of point on any surface of the sphere. In fact, it can even not touch the sphere. It's possible to have states that kind of shrink or are less than 1, but that's what we call a impure state, and you encounter that when you start to learn about quantum or the effects of noise on quantum systems, because then we start getting these imperfect superpositions, and you can simulate or make noise simulations when you perform certain computations. But I think for now we just live in la la land, and we believe that the vector is guaranteed to always be 1. It's always going to touch the surface of the sphere. But when we perform a measurement, the vector has to collapse. It's going to be in 0 or it's going to be in 1. So that sphere essentially just turns into this line. You're either here or you're here upon measurement. And the way we can express that measurement is the following. So if I have a vector that I'd like to measure the probability of it being in, so for example, I have this vector. So this vector is kind of, it's leaning more towards 0. So intuitively, we can say, okay, the chances of it at being in state 0 are a lot higher than it being in state 1. So I could have this x here be ket 0, and then I could have this bra here. This bra is my quantum, whatever state I'm in. So if this psi, so you notice here I have ket psi, well, I have to convert that into a bra. I convert that into a bra, and then I multiply that times the ket x here, ket 0 or ket 1. That becomes the way with which we're measuring it. And then you see I take the absolute value and square it. And that tells me the probability that I'm going to find the state vector upon measurement in this other basis vector. So you'll note that this notation gives us a degree of flexibility. Like in a lot of quantum computing tutorials, we assume, okay, you can only have a result that measures, in the 0 or 1 basis. But it's not uncommon to say, if I could get the state vector for this guy here, so it's on the y-axis, I could also measure the probability that the vector might have been in this position. And that's what we need these bra vectors for, is just a way to perform these measurements. So you see p of this basis vector, so the probability that we will be in that quantum state. Now, there's a similarity I wanted to point out with this vector, and this sort of goes back maybe 2 or 3 weeks in workshops, and it's how you would find the position of a particle given a continuous wave function. So remember, these vectors are the vector should not be equatable to the wave function. It is a quantum state, whereas the wave function is this continuous, all-encompassing description of a quantum system. So the state vectors are just a nice way to kind of focus on the thing that we're interested in, because we don't really deal too much with momentum in a quantum computer. It's just a non-applicable property, or non-applicable observable, if you remember your lingo I kind of dropped in the last workshop. The similarity with this notation here, this stuff here, and the stuff that I presented last time, where I said, okay, if we take the absolute square, so if I take the conjugate of the function times itself, so I get this property here, this will give us the probability distribution of where the particle is. And this kind of, so if you recall, we had to use separation of variables. So I had the Schrodinger wave equation, and when I solved it, it's a second order partial differential equation. And so I separate it into the time-dependent components, and then I have the time-dependent and space-dependent components. So the time-dependent we didn't really care about. I kind of tossed it to the side, because the space-dependent components help us solve the different energy levels. And from that space-dependent component, we were able to naturally realize that the energy levels are, in fact, quantized. And you'll notice this notation, I intentionally call it sloppy. And it is sloppy because you don't see the psi of x. I've omitted the fact that there is a position basis in here. But when we work with our sort of in quantum computing, it becomes very important to understand. Yes, okay, the state there's an associated basis vector that you need to have made explicit. But I just wanted to show that there is a parallel between why it's advantageous to know the underlying quantum mechanics and where it goes in the context of quantum computing. So this is one of them. And this doesn't have the bras and kets on it, but it's very easy to see because this conjugate, once again, the conjugate is represented by, if I were to take the bra, and then the ket would just be the normal side. So conjugate would give me the bra and then the ket, and this is essentially an equivalent expression to what you're seeing here. Granted, the X is implicit, so once again, that's what I would call a bit of sloppy notation, but it just looks nicer. Okay, so with all of that review out of the way, we can kind of get into these gates. So what are quantum gates? Gates are how we manipulate quantum states. So quantum states are given their own ket, and if you remember, the ket is a 2-entry vector, and that 2 entries are sort of like the coefficients here, telling us, okay, how much in 1, how much are we leaning towards 1, and then how much are we leaning towards 0? That's how I always like to think about it. Granted, that's not an entirely accurate description, because as we'll see later, it's a sphere. It's a block sphere, not a block circle. So there is a bit of additional information we can encode, although that information is not exactly the easiest to kind of keep a handle on. And in our next workshop, I'll go into a lot of circuit identities which take advantage of what we call phase. So phase is the rotation of this vector along the sphere. So that phase lends itself to a lot of very key properties that you will see, such as probability amplification, which you'll see with more advanced algorithms like Shor's and Grover. Those will be for the later workshops. So our gates are represented as matrices, and they have some special properties, one of which I mentioned is that they're unitary. So what do I mean by a unitary matrix? Well, it has to have one of the consequences of being unitary is that if I apply a transformation of my state vector using a unitary matrix, that state vector is, I can find another matrix or series of matrices that will permit me to return to my original location. So it means that it's a reversible operation. In fact, all the gates that we use in quantum computing have to be reversible. Now, the dimensions of the matrix are very important because they have to match up with the ket. Like matrix multiplication, you always have to make sure that the rows sort of match the number of entries in your columns to make sure that the multiplication can go through. Otherwise, you have these inappropriately sized dimensions, and then you can't perform any manipulations. So, to apply a gate to a certain quantum state, we're just going to multiply the matrix with the ket. So the ket was the column vector, and the matrix is just it's just representing the transformation of that ket. We perform the multiplication, and that's all there is to it. And I understand the majority of us have used a lot of quantum computing frameworks, and they always have like a built-in unitary simulator or state vector simulator. That's all they're doing. It's just high performance matrix multiplication or vector multiplication. And that's really all there is to the simulation. In fact, it is so easy to kind of grasp this idea that I've actually written a little miniature simulation library for us to play with. And I think it'll help us in kind of visualizing what each gate can do and their relationship to each other. So one of the first series of gates that I want to represent are the XYZ gates. And they represent sort of a pi radian rotation around each respective axis of the block sphere. So remember, the sphere has an X, Y, and Z axis. Well, we have these corresponding gates, poly X, poly Y, poly Z. This also goes by the name of just NOT, or like the X gate, the NOT gate. It's the quantum equivalent of a binary NOT gate, and that it inverts your state. So if I was in state ket 0 or state 0, I'd be in state 1. And if I was in state 1, I'd be in state 0. And we'll see that very soon why that is the case. And just as a very cool side note, these matrices are not just something that exists in the realm of quantum computing. In fact, these matrices are direct ripoffs from the Pauli matrices from quantum mechanics. They're used to manipulate, I believe they have a relation to certain spin systems. So I haven't talked about what spin is. It's another intrinsic quantum property. But the Pauli matrices come into play when you're dealing with spin. And these matrices existed long before quantum computing was even an idea. But they have a very beautiful and elegant translation into the realm of quantum computing. So hence, another argument for why I always support the idea of teaching just a little bit of quantum mechanics before we go into quantum computing. Now, it's no good just kind of seeing these, these little symbols here and these numbers unless there's some kind of visual analogy. So I've developed a number of sort of visual examples of what's kind of going on here so you can see just exactly what it is. So this is NP Quantum. NP Quantum is that little library that I made, and I just call it NumPy with quantum extensions, essentially. I haven't bothered to publish this thing considering how messy, and I'm pretty certain that any those more advanced in quantum computing would frown upon my practices, but I'm willing to do what's necessary to help you kind of visualize what's going on here and really see for yourself that it really just boils down to a bunch of vector and matrix manipulations and multiplication. All right, so we'll go ahead and import this guy real quick. And then here are the basis kets. And you'll notice that internally, you might get confused about why I chose matrix. The reason is it's a Python limitation to the library that I'm using to represent them. But you'll see it's still you can still treat this as a column vector, 2-entry column vector. And if I plot this ket 0 onto the block sphere, you'll notice we are pointing straight up. So that is our 0 state. And for ket 1, we see that the 1 is kind of switched. So if I just show you once again ket 0, so you notice that all they are exact opposites of each other in terms of the values here. If I plot our 1, you see the 1 is at the very bottom of the sphere. So 0 is pointing to the top, 1 is pointing to the very bottom. So that's that's all well and good. So now we can see what our x, y, and z gates do. So once again, just to remind you, 0 is at the top, 1's at the bottom here. Now I'm going to apply the x gate here, and you notice, okay, I just multiply the ket by the x. Now you might be inclined to ask, well, why can't I do it this way, ket 0 times x? And that has to do with how matrix multiplication works. In matrix multiplication, the order is incredibly important, especially when it comes to the dimensions, because it's the you have to make sure the dimensions match up, or the multiplication can't even go through. So that's why we have to put the matrix on the left side and the ket on the right side. So that's just it's just math. That's all it is. It's just a limitation of the math. And just to prove to you that I'm not doing anything particularly fishy here, the x gate just looks like this matrix. So 0, 1, 1, 0. So this is the exact same matrix that I had on display here, 0, 1, and 1, 0. And what's going to happen here is if I start out in this 0 position, notice the x-axis is right here. And I mentioned that all these x, y, and z gates perform a pi radian rotation. So it's going to rotate pi degrees along the x-axis. So we're going to be sitting here. And that's why it's called the NOT gate, because it just inverts whatever state you're in. So here we go from 0 to 1. So we just made that 180-degree or pi radian rotation from 0 to 1. And if I were in 1 and I applied the x, then I'd be back in 0. And just to sort of show you that, I can just open this new cell here. I'm going to go ahead and copy and paste this guy. So let's do ket 1, and I'm going ahead and there we go. So ket 1 would originally be pointing downwards, but I applied the x gate, rotate pi radians on the x-axis. So now we're pointing at 0. So that's what our little x gate does. And we'll notice that you can already see the y-axis, and then there's the z-axis isn't labeled, but it's just it's just right here. So y is here and z is there. So the y gate is just going to perform a rotation along the y-axis. So here we go with y, and then I apply ket 0. So 0 would be the vector here, and then I would just apply that y gate through matrix multiplication. And I've printed, if I go ahead and run this, okay, here we go. And you'll notice we went from 0 to 1. Now you might be thinking, wait a minute, that's the exact same thing that we saw with the x gate. And you're right. And it has to do with just the fact that how the axes are arranged. I mean, if I were in 0, a pi radian rotation along the x-axis brings me to 1, but along the y-axis, it would also bring me to 1. So they essentially perform the same kind of, a very similar property. Granted, if I were to shift the vector, so maybe if I made it point, I point like maybe pi over 2 radians to the left here, then you would notice very clearly that it's a rotation along the y-axis for that y gate. And once again, it's a pi radian rotation. So, I said it's somewhat hard to see the distinction, so let's try a more obvious state. Now, I won't introduce what ket plus is just yet, but just know that it's a state where the vector is kind of just sitting. It's just sitting on the x-axis. And you also notice that it's a perfect superposition where we're right in between 0 and 1. So we're just kind of, we're just kind of chilling out in the middle between the two of them. And if I apply that y rotation, so let's think about this before I even show you. It's a 180-degree rotation along the y-axis. So that means that the resulting vector should be on this side. It should be on this side. So we go from this side to that side. So let's see if my hypothesis is correct. And lo and behold, it is. So that's thinking about these gates visually is incredibly helpful. And the z gate, as you can expect, is a rotation along the z-axis. Now this is even harder to see than the other ones because ket 0 and ket 1 both lie in the z-axis. So if I perform a rotation, it's going to be the same vector, so you don't really see it. But if this is another function I implemented, ket from angles. This lets me generate any arbitrary sort of quantum state on the Bloch sphere. So I generate this one, and what does this mean? I'm saying originally I would like this new state to be pi over 2 from the top to the middle of the sphere. So that's pi over 2, and then pi over 4 rotations. So I'm just gonna rotate this guy over. So I haven't applied anything here. But then if I apply z, you'll notice that I've rotated 180 degrees. So this is the original vector. A rotation of 180 along the z-axis brings me here. So if you're just playing with ket 1 and ket 0, it doesn't become incredibly apparent what exactly these gates do until you start messing with what I call non-trivial states, where you're sitting in the middle of the sphere or you're kind of tilted in some odd way away from 0 and 1. And then you apply it, and then it becomes incredibly apparent what the difference is. So those are our x, y, and z gates based off the Pauli x, y, and z spin matrices. Then we get to the Hadamard gate, and the Hadamard would be represented with a little, we'd get a box and then there'd be an H in it. So that's what a Hadamard would look like. And it is the heart of many, if not all, quantum algorithms. So if you were to look at the Bernstein-Verzani algorithm, or even, I think, Deutsch-Hose, you will need to use a Hadamard gate. And this allows us to get into what I call the perfect superposition state. What do I mean by perfect? Well, it means you're 50-50. So ket plus, the thing I just showed you with the vector that's sitting in the middle of the sphere, is in fact what you would get from applying a Hadamard to ket 0. And I'll prove it to you very quickly here. So if ket 0 would be here. If I apply the Hadamard, I'm sitting in the positive x direction. And if I apply it to ket 1, I'm sitting in the negative x direction. Now you might be tempted to say, oh, it's just a 90-degree kind of rotation, right? I could maybe come up with another rotation gate, and that's not entirely true. There are a number of fundamental qualities about that Hadamard gate that make it very useful, incredibly. But for now, in the context of just a single gate on a single qubit, that's all it does. So if I'm in 0, I go to the positive x-axis. If I'm in 1, I'd go to the negative x-axis. So we see here, not phase gates, excuse me. So yeah, ket 1, I applied ket 1 here. So we're going to be here, and ket 0, I'd be in here. So that's what the Hadamard does. And you'll see I'm definitely underselling that gate, but it should become quite apparent rather quickly how important it is. Now with the Hadamard out of the way, oh, and I guess I neglected, okay, this is a little bit on my part, to show you that this is the actual, you get this plus and minus state. And you'll see this very frequently in quantum computing papers or just general tutorials. That's just, so if I'm in 0, I go to plus, and if I'm in 1, I would go to minus. And you see that it's, 0, 1 over the square root of 2 times 0 plus 1 over the square root of 2 times 1. And 1 over the square root of 2, you can kind of treat that as just 1/2, because you remember the condition for the coefficients alpha 0 plus beta 1. So if I take the square of that, and then I were to add it, it still equals 1. So we're still pointing within the sphere. We always have to make sure that we kind of normalize our vectors. So now we can get onto the phase gates. And I guess I'll kind of front load you guys here first. And these perform rotations around the block sphere. And these rotations are not exactly the X, Y, and Z rotations that I showed earlier, which are just fixed at 180 degrees. If we only had X, Y, and Z gates, we could not perform, and Hadamards, we still couldn't perform all of the necessary computations that we'd like to see in quantum computing. So a lot of the gates that you'll be seeing here originate from what we call an R-phi gate. So what R-phi actually is a matrix, and that matrix you can plug in a value in radians, like pi over 8 or pi over 16 or pi over 3, and that matrix will generate some rotation along the z-axis. So you remember that 1 and 0 are just sitting on the z-axis. So if I were in the ket plus position, I can rotate freely around the z-axis of that block sphere. So some common variants of R-phi are the S gate and the T gate. And the S and T's have their own variant called S dagger and T dagger. And we'll see why it's called dagger very quickly. And I just wanted to point out the pattern with the gate and its quote unquote dagger form. So if S is equal to the square root of Z, and you're like, wait a minute, why the hell would we call it the square root of Z? It's because if Z gives me a pi rotation along the z-axis, but taking the square root of Z just gives me half that rotation. So if it was pi, now it's pi over 2 essentially. And the dagger is essentially the conjugate transpose. It's the Hermitian of the S matrix that puts square root of Z in the other direction. So Z is always going to go like, in the positive direction. Well, if I take the square root of Z, so it's pi over 2, but then it's pi over 2 in the other way. And I'll show you in the main. I'm just kind of front loading you guys with this information. And then T is an even shorter variant. It's pi over 8. And then we see T dagger is just negative pi over 8. So, it doesn't really help to just hear me talk about it. Why don't we actually kind of, see this in action? So here are phase gates. So I remind you, ket plus, or that's why I call it ket plus, by the way, is because of that notation where it's just a Hadamard applied to 0. So this would essentially be, let's see, if I had 0 here, and then I were to apply the Hadamard here. So Hadamard times 0 would give me ket plus, and it would just be sort of pointing right here. So here's R-phi. So you see I've implemented it as a function, but I can essentially plug in something like np.pi. So a pi rotation. R-phi with a pi plugged in is essentially just the Z matrix. And you can actually visually see this, like just from the mathematical notation here, because the matrices for Z and R-phi are pretty much identical. And you're probably going to have some objection here because you're looking at this entry and you're like, wait a minute, that does not look like a -1. And the truth is, Python and a lot of programming languages, they always have some numerical rounding error. So if you look even closer, you'll realize, oh, it's -1 plus 1.2 times 10 to the -16. So it's an incredibly small value. And that's just a consequence of computational error. If I was being very precise, I could clean up some of the code in my personal library here, and then I could, get rid of that error. But it's always nice to remember that quantum computing is still a rather imprecise science. So that R-phi, it's our generalized rotation matrix along the z-axis. So then we can generate S, or the square root of Z. So let's see if I can actually, if I put S here, okay, this is sort of the matrix. It doesn't really help to see the numerical values, but if I just do S times ket plus, so our S gate, notice it's a rotation. The full-on Z gate would go all the way to the back end of the x-axis, But since S is also known as the square root of Z, we note that we only go halfway. But notice that just like any squared value, or square rooted value, if I multiply it with itself, you get the original value back. So S times S actually, it makes another rotation, and it goes here. So this is essentially the equivalent to a full-on Z gate. So essentially, S times S is equivalent to Z. And that's why we call S the square root of Z gate, because you're going to immediately see, if I had the square root of Z times the square root of Z, well, that should just give me Z. And that's not even, that's no fishiness in terms of matrix or vector multiplication. That's just a consequence of arithmetic. So that's kind of nice to see. And I've shown it here. Z times ket plus gives us the same state. And then S times ket plus gives us the same state. So that sort of clears up why we call it the square root of Z gate. And then we have S dagger. Okay, so what exactly is S dagger? So I think it will behoove us here to kind of see this. So S is this matrix here. And then if I show S daggers is this other matrix. And okay, it doesn't really, you don't really see any major differences here. At least visually, it's not very convenient. The only difference you can sort of detect here is that the sign in front of the complex component has been flipped, which should give you a hint that the dagger here means take the conjugate transpose of that matrix. So let's look at S again. And then if I were to do this, S dot conjugate dot H. So this is NumPy notation. So take the conjugate of the S matrix and then take the Hermitian of that. And you'll notice that we get the same properties. I just transformed the S into the S dagger here. Oh, wait a minute. Or S dagger into S. Yeah, okay. Okay, sorry, that's a little, that might have been a little too fast. In fact, I might have even done something wrong there. But essentially, that's what's supposed to, like the relationship between S and S dagger is that you've just taken the conjugate or the Hermitian of the matrix. Or actually, let me see this real quick. Let me confirm this for myself. If this doesn't work, S dot H. Oh, okay, Amir. Amir's right. I should probably, because it is non-Hermitian. Okay, that is definitely, Amir brings up a good point. But that it is a unitary but non-Hermitian gate. And that is absolutely true. In fact, we can see that it's non-Hermitian because if I do S dot H is not equal to the S dagger gate is not equal to the inverse of the S gate. And that's one of the reasons why in the very beginning I emphasized that I didn't explicitly mention this, but I did mention that every gate is reversible, but it's not required that each gate is self-reversible. It's unitary, and then X is equal to its inverse, which is equal to X dagger. Yes, Amir sums it up much more nicely than what this little mess that I'm doing here. So Amir, thank you so much for pointing that out. I do genuinely appreciate that. We'll go ahead and just kind of like clean this up a little. Yep, S and S dagger. So S dagger is not equal to the inverse of S, and that's just that has to do with the fact that it's non-Hermitian. Now, with that being said, if we take a look at S dagger, notice it goes the opposite way of what S did. So if S goes to the y-axis in the positive direction, S dagger is just going to bring us to the other side. So we went from here, and now we're going to the other side. And if we keep making these successive applications of S dagger, well, we still get to the Z, like we still have the effect of a Z gate, but it takes two S daggers to apply that. And then we'll notice, let's see, I think the rotation gates here. Okay. So all those rotations were focused on the Z-axis, but that's not, those aren't the only rotations. In fact, you can actually see we can actually have arbitrary rotations around each axis. So Rx, Ry, and Rz. And these I won't focus on too much, but they are sort of easy to implement. They have their own matrices, but essentially those are generalized gates. So they'll take a parameter, like I chose pi over 3 here. Or no, I set up this original vector here. And then if I say, okay, rotate along the x-axis by pi over 2, so then you see that we kind of make that move along the x-axis. So it was pointing upwards, pi over 2 brings it kind of on its side. So now it's sitting on the xy plane here. And we have ry and rz, which will also perform. So this is another arbitrary configuration I've pointed out. Yeah, ry times ket plus. That's ry times. So ket plus would be sitting here on the x-axis, and then I apply the y rotation with a pi over 3 degree. So then it just brings it down pi over 3. And then there's also a z rotation. So the ket plus would be here, and then I just rotate that along the z-axis by pi over 7. So it's kind of sitting here. That's what I meant to show earlier. So we can rotate along the x and y axes with these other gates. And that sort of brings me to this idea of universal quantum gates. So a universal set of gates, if I give you any configuration, I can boil down that configuration into a series of these universal gates. Now, intuitively, this shouldn't be possible. And why do I say that intuitively it shouldn't be possible? Well, let's sort of go back to this picture here. This is a sphere. Now, if you notice, like, a sphere has a lot of points, an infinite number of points on its surface area. So when I make this statement that you can take any point on that sphere where any quantum operation can be reduced into a set of gates, I'm literally telling you that if you give me like just a finite number of gates, I can guarantee you that I can get to any infinite sort of point on this sphere, which isn't necessarily true. It actually isn't possible, but there is a theorem, and this theorem is very crucial to how we work with quantum computer today, and it's the Solovay-Kitaev theorem. Now, this theorem has roots in quantum mechanics. It was not originally intended for quantum computing, and this has to do with group theory. Group theory is another field of math that can get very involved. You see it a lot in quantum mechanics. It's how we help sort of categorize properties of particles and their operators and commutators, and I won't go into any of that, but the idea is that we can generate an arbitrary approximation with the series of gates efficiently. This efficiently has to do with a bit of it's a rather sensitive to the computer science terminology. When we say something is efficient, we mean we can do it in polynomial time. So given an operation that is length n, then the number of gates will grow polynomially with regards to its input. That's what we mean by efficiently. And what do I mean by arbitrary approximation is, let's look at the sphere, right? And let's say I'm pointing here. So if I'm pointing along the YZ plane, and I say like, okay, I want to get my quantum state to be on that point. So with the Solovay-Kitaev theorem, I can generate a number of approximations. So I could get closer and closer and closer to that point. Now, I might not be able to get exactly to that point, but I can get so close or to a desired degree of closeness. That's what Solovay-Kitaev guarantees. Because it is technically impossible to get exactly to the state that we want given a number of basis gates. Because it's a finite number of gates and an infinite number of superpositions that we'd like to kind of target here. So that's what the Solovay-Kitaev theorem means, is we can boil things down essentially. And there are different sets of universal gates. A very common one is the Clifford gates, which are the Hadamard, the S gate, and the T gate, and C naught. Now, in this workshop, I'm not introducing C naught yet. That's actually planned for the next workshop, where I expand to 2 qubits and beyond. And hopefully in that next workshop, I will have that. I won't make a mistake like what Amir caught with getting unitary and Hermitian mixed up. Despite all the work I've done, I still do manage to get some mistakes slipped in there, which is why I still like visualizing things. So that's why it's just something to be cognizant of. And we also have IBM. IBM has its own set of basis gates, and these look really weird. U1, U2, U3, I, and CX. And these don't really seem like things I've shown you yet, but in fact, these U gates are what we call generalized gates, in that I can plug in, how I had a function, a kind of custom function, that would let me generate any arbitrary point on this block sphere. Those U1, U2, and U3 kind of act that way. U3 is the most general. U2 and U1 are actually sort of restricted subsets of the U3 gate. These are specific to the IBM systems. I don't really see them too often outside of the IBM systems. But then we have I. I is just the identity gate. So what does the identity gate do? given a state, it gives you the state back. And there's some reasons why we want to have that around. And then CX is is just another way of writing controlled knot. But you'll see the CX and C naught in the next lecture or the next workshop. And by the way, a cool thing to mention though is when you're making your quantum circuits and you're putting together all these gates, the number of gates that a quantum system or quantum computing platform supports is actually a lot smaller than what the system provides. Like when I'm writing the code, I might use, Hadamard, or not a Hadamard, a T gate, but I might work with a system that's like, oh crap, I can't support a T gate, but I can support these gates. So the compiler is smart enough to take the single gate and decompose it into a number of other gates that kind of simulate that one gate that you wanted. So that's something to be cognizant of. And that's why there are these why I wanted to bring up or wrap up the idea with universal quantum gates, that we essentially have, all these unitary matrices, but a platform might not be able to implement all of them. So it boils those certain matrices down into the ones it can support. So you'll notice in a lot of quantum papers and tutorials, there's a distinction between the universal gates and the hardware realizable gates, or these are what they just call hardware gates. And that's especially true for, ion trap systems, superconducting systems, what Xanadu is doing with their rather hard to understand, but still really cool platform with their continuous variable system, which, I personally am still kind of, wrapping my head around. But up next, so we'll be expanding to 2 qubits and beyond. And once we nail down those 2 qubit gates, then I can actually talk about a number of very, very counterintuitive, but very powerful circuit identities. So, in electrical engineering, you learn about resistor networks and, how if I arrange switches or power supplies in a certain way, there's a repeated property of that arrangement. So in an equivalent manner, you will see that with these quantum circuits. And, I emphasize you're going to start seeing some really, really weird stuff. So the Bloch sphere is, when we're living in the 1 qubit world, things are, fairly nice. There's a nice geometrical analog. But once we go to 2 qubits and above, the Bloch sphere does start to kind of break down for representing those states. And it does become rather nasty. At least for your intuition. Quantum mechanics is the bane of existence for Newtonian mechanics, which our intuition is based around. But hopefully with more of these workshops and more experience, we'll be able to develop what I was really shooting for in the very beginning, which was a quantum intuition. That's the sort of sweet spot. So with that being said, that's all I have in store today. With that being said, I'm opening the floor to questions or concerns or any corrections that all of you would like to make for all the things that I've said. So feel free to unmute, speak openly, and I would be more than happy to answer your questions.
John, you're way too hard on yourself. I learned so much from you, and I'll tell you, I've referred back to the sheet where I had to write down the difference between Hermitian and unitary. I refer back to that so often until it commits to long-term memory. But what's interesting, I think you were just off by a little bit. So your approach of going with S dot conjugate dot H, I think you can just do S dot H.
I think you're right about that.
Yeah, because I just looked up, I wasn't even aware of S dot H, so I looked at it, and the H is just the conjugate transpose. Now, when you were doing this is like the conjugate transpose multiplied with whatever matrix has to be equivalent to the identity, because that's the property of it being a unitary.
Right.
And so when you did that both with S and S dot H and S dagger, like even if you multiply S times S dagger, that would also give you your identity because it's unitary, I believe. Yeah, if you don't mind, like we can maybe sort this out a bit, because what I'm trying to understand too is why NumPy calls that. Did that give you the same? Yeah, cool.
Yeah.
So yeah, what we're looking at here, I think, is just the unitary property, which means that you have an inverse for your operation that gets you back to identity. Now, whether that inverse is the matrix itself or not is the Hermitian part of it. So if, with x times x is identity, but yeah, there's no x dagger. Well, x dagger is itself, right?
Right,
Yeah.
right.
So then what I'm wondering is why NumPy calls, so going back to, you were starting to play around with S. You did S dot conjugate dot H. And I think all you have to do is S dot H.
Yeah, in fact, I think I realized that S dot H,
Yes.
S dot H would be the equivalent of, I think I meant to put
Yes.
dot T.
Yeah, okay, there you go. So
Yeah,
that's all it was.
Yeah, so thank you so much for catching that. And I guess like yeah, I mean you were able to tell. I'm using NumPy. I think it's just a bunch of I've over time, as I've played around with like trying to understand all these different circuits, I've collected this rather cluttered library of these gates that I use to kind of help myself visualize it. Just because if I do pen and paper, it's kind of it's time consuming.
Yeah. Now, what confused me was why they call it the Hermitian operator. And I think that actually has nothing to do with it. Well, maybe not nothing, but it's not the same as a Hermitian matrix. So the Hermitian operator is that conjugate transpose. It doesn't imply that whatever you're doing it on would be Hermitian.
Right. It's just something you can apply to anything else, especially when they use that operator terminology. It's like, oh, okay, it's I always thought of operators, especially in context of quantum mechanics. An operator just takes a function and gives you another function, and that's all the operator would do. And so yes, there is no assumption or presumption that it is Hermitian to begin with.
Yeah, cool.
Thank you very much for clearing that up. I just realized, like, I just saw that and I was like, oh, wait a minute, that's not right. I think I meant to do conjugate T, and then S dot H is just a shortcut. In fact, that's one of the reasons why I originally why I wanted to like put the kets. If I go all the way back up here, you see my ket implementation is a matrix, which is kind of weird because I said it was a vector, and NumPy has an implicit vector support, but those vectors don't support the dot H operator. So I wanted to like keep all the really nice matrix tools. So I was like, okay, I'll just pretend it's a matrix for now.
Oh, that's cool. Yeah.
Yeah. So thank you very much for pointing that out.
Sure.
I think we have new people from people I've never seen from our prior meetings. So to all of you new faces, thank you so much for coming. And hopefully this was useful to you. I definitely hope is able to give you some clarification or value.
It is useful, John. Thanks.
Well, thank you so much for for always coming to these little meetings.
Oh man, I'm learning a lot. It's interesting though. I was just thinking, it's kind of, speaking of physics, it just reminds me of what's that guy's name? Einstein, right? As we're all learning this stuff, we're all moving at different speeds, and it's all relative, right? So, you're cranking right along, and I'm just trailing along in the vapor fumes afterwards. But I'll catch up eventually. But very helpful. It's amazing, little things like Hermitian operator and Hermitian matrix. I just thought they were the same thing.
Oh no, I mean I've definitely
they're not.
Yeah, I've definitely had that confusion before. I remember, in fact, the reason why I was so like I'm still sort of error prone to it, or why I wanted to like do that little demo, was because in the last quarter, I actually had a workshop set up, and then I was like, okay, it's going pretty well. And then the next workshop, and then I realized like, oh crap, this is not the right terminal. So I had to put like a little addendum saying like, okay, there's some errata with the prior material, and then like, here's the distinction. And I think I had like a whole nother workshop, just like, okay, here's the clarification. Don't get these mixed up.
Yeah, well, you'd probably be the first person to do that, because I've never been able to figure. I just assumed they were the same thing. That's one of the things the challenge is when you're learning a new field, the vocabulary, little things like that, you get bogged down on it, and it's hard to, just work past it, but cool.
Oh yeah, absolutely. But I mean, it also lends itself to some nice properties. Like when I was learning about the X, Y, and Z gates, prior to all that exposure to quantum computing, I already had like a little bit of familiarity with some of the quantum mechanics stuff. And I was like, okay, I've seen these matrices before. And I was like, the poly matrices, which is why IBM and a bunch of other companies, it's kind of sort of tip of the hat to them. They'll say it's the poly X gate or the poly Y gate. And or if you really want to get advanced, and I didn't know these matrices before, but they have a very strong physical basis, which are the Ising sort of coupling gates. And then you get into like the Ising model, and those are used in the ion traps, because the way the ion traps are designed, Kirk's having a bit of a fit over this naming scheme, but the way the ion traps are designed are in such a way that these Ising gates, so Ising XX, Ising YY, Ising ZZ, are naturally realizable. So we would call that a hardware gate. And when we're like writing all of our advanced quantum circuits, we can translate a lot of the actual unitary gates that should be available to us into the hardware realizable gates. But that was a total, just a footnote that there are such natural like name relationships between quantum mechanics and what we see in quantum computing.
Good footnote. Thanks.
Absolutely. All right. Let's see if there are any more questions or concerns. I'll give it like another minute or two, and then I'll go ahead and then I'll end the meeting. And after the meeting, I'll try and get the recording up as well as the slides. And once that library, as I loosely put it, gets kind of tidied up, I'll definitely put it up, and maybe you guys if you derive value from playing around with it, because I know it definitely helps me, like when the textbooks kind of just wave their hand like, oh yes, it's a matrix multiplication, and then like the matrix multiplication has this result, and I don't know, but I think the sign of any good engineer or any good scientist is to not always believe every single thing that it's always good to kind of prove for yourself. That's the best way you can learn something, is to prove it to yourself. That's why I had that whole Python library with the block spheres and the matrices, was to prove to myself, like, okay, that's where the state vectors come from. That's where we get the rotations on the block sphere, and that's you've sort of made it your own. You've turned that knowledge and internalized it. But that's just a sort of long-winded aside from me.
Agreed. Not the long-winded part, but what you said. Yeah. Just doing it. That's the best way to learn it.
Yeah, absolutely.
That's how I internalize it too. I write code. Once I get to write code, I know it better than anybody.
Absolutely. I think that's one of the great things about if you ever like just learn to code, is it's so interdisciplinary. I mean, there's so many fields that just leverage existing software packages, and in fact, I know, like back in high school, I was terrible with math. If you want to get an idea, I almost got like B's and C's. Like it was abysmal. I sometimes wonder why.
Oh, you're terrible. Yeah.
I sometimes wonder why UC Davis would have accepted me on those grounds. But anyways, there's another obscure language called APL, and APL is where every keyword is a Greek letter, but you can do all these matrix manipulations, and those languages, like coding, motivated me to learn these subjects better, and now my math is a lot better. It has to be better to understand the stuff in quantum computing.
So you're saying that APL improved your math?
Yeah. It was I still have the APL manual. I paid $50 for that thing, and I love it. I love the language. It's awesome.
Most don't even know what it is.
I think it's one of the true gems out there. I love it.
Yeah.
In fact, I was thinking of I was already halfway through this, but I was porting that quantum library to APL just because of how elegant it is to work with matrices and linear algebra in that environment. I love it. It's a guilty pleasure of mine. All right. Well, I guess that wraps up the 5 minutes, and I don't think there are any more questions. So thank you so much for coming to today's meeting. For all your feedback and questions. And I'm really looking forward to the next workshop. We will definitely see some really spooky but unique phenomena in action, and that will kind of help solidify our understanding of things. So once again, thank you so much. I hope you all have a wonderful weekend. And I'm going to go ahead and kind of stop the recording and end the meeting as well.
Thanks,
Thank you
man.
for coming.
See you all.